But for this definition, the limit equal to 0, this you could not write this by this way. If you write the limit 0 in this way, so this is wrong. You could not write this way because H is an element in the ball. H is an element in the R neighborhood of the origin. So H itself is a point in Rn. It could not appear here as a denominator. Okay? The norm of H is a real number. It could be denominator. But H itself is not. Okay? This is delicate, but without knowing this, you could not understand what we are talking about. Okay. So I want to say to study this course and also other course in mathematics, it is very important to thoroughly understand the concepts you are encountered. Okay, and whenever possible, you should consider the geometric meaning of the concepts. Once you get the crucial points of the concepts, which I had mentioned whenever we encounter a new concept. So once you understand the points of the concept, everything will be easy. Okay. So for example, in our quiz problem 3 in our quiz, we have a continuous map. Continue. And satisfies this condition. X goes to infinity. The norm of fx is infinity. Then you are required to prove that the range of f, the image of f, is closed subset of the codomain Rm. Okay, we have this problem. So we are required to study this set and to demonstrate that this is closed. So you need to know what closed set means. A closed set means that for a sequence yk in this set, if yk converges to some point b, then b also in this set. If this property is true, then by definition, this set Frn is closed. But because yk is taken from Frn, of course you can find an xk in Rn such that yk is fxk. Of course this is true, but many students after choosing this yk, he said or she said xk converges to x star. This is wrong. You don't have xk converge to x star. From the convergence of yk, you could not obtain the convergence of xk. Okay. For example, if f is a function n equal to 1, so we define fx is 0. The constant function is continuous. So if yk belongs to the image of f, which means the image, because for every x, fx is 0, therefore this image is 0. Okay, but that is any sequence. This means yk is 0. But for any xk in Rn, for any x in Rn, fx is 0, is yk. So if this is true, if you can deduce from yk converge to b, the fact that xk converge to some point, then you will get a absurd conclusion. Any sequence in Rn is convergent. Of course, this is not true. Okay, so I think you write this wrong statement because you don't understand what closed set means. Closed set means whenever y can converge to B, B belongs to the set. This has nothing to do with the convergence of xk, of the corresponding sk. But you misunderstood that this implies the convergence of xk. So this the reason for this mistake is that you have not understand the concept of a closed set very well. Okay. So also in the proof of this problem, some student after getting this xk, they want to prove that xk is bounded. So they argue by contradiction. They assume unbounded. Then they say xk goes to infinity. This is also wrong. Because a sequence can be unbounded but not approach to infinity. For example, our xk, take xk to be k1 plus minus 1 to the power k. The first component of xk is given by this, and the other component is 0. Then obviously this xk, the norm of this xk is unbounded. Okay, but it is not converging to, it is not approaching to infinity, because when k is an odd number, the xk is the origin. It has infinitely many terms remains at the origin of the space. Therefore, this sequence is the norm of this sequence does not go to infinity. Okay, so this means you need to enforce your logical training. The logic, your logic has a problem. Okay, so this is what I want to remind you from the first several questions I have graded in the quiz, and I found you have this problem. So I hope you can take this in mind, and to improve yourself of this and other aspect of your study. Okay. Now, last time we studied the chain rule. Chain rule. This is an important theorem. Chain rule. So this says that the theorem says that G is a map from a neighborhood of A to Rn, and F is a map from U to another Euclidean space RL. So if G is differentiable at A, and F is differentiable at the corresponding point, say denoted by B, the image of A under the map G. U is our U here is a subset of Rm, and also we assume that the image of G is contained in the domain of definition of F. Therefore, we can have a composition. The conclusion of the theorem is that then the composition is a map from the R neighborhood of A in Rn to RL. The composition is differentiable at the point A, and also we know that the derivative of this composition at the point A is the derivative of F at the point B multiply the derivative of G at A. So this is the chain rule. Okay, we have a metric form. Both sides of this equality are matrix. The left hand side is L by a matrix. the right hand side is L by M and M by a matrix. Therefore, both sides are L by a matrix. Okay, then this is equality for matrix, so it has this form. We write this and every entry of this we write in our last lecture. I will not repeat it here. But if we use X to denote a point in BRA and use U to denote a point in the set U and use Y to denote a point in RL, then our G maps X to U and our F maps U to Y. So the composition maps X to Y. So the derivative of the composition is regarded to the partial derivative of Y to X. Okay, but Y has L component, X has N components. Okay, X has N component because X belongs to the n-dimensional ball BRA. Okay, so we have a formula: dy I dxk is dy to duj to dxk, j from 1 to n. Okay, so this formula is the why we call this a trend law, because intuitively it seems that we can cancel the dyj in the denominator and the numerator to get dyi over dxk. Okay, roughly speaking. Therefore, this is called trend law. Now we will apply this trend law to compute some derivative of composition of functions. Okay, I will use this example to demonstrate the computational technique. So we consider this function. The first example, U is f x y, y over x, and yz. This is a function of x, y, z. Okay, but this is not the same as U equal f x, y, z. Not this. What this mean? This means this function U as a function of x, y, z is the U as functions of x, y, z is the composition. So x, y, z, firstly, x, y, z is mapped to some point x, y, y, x, y, z. Okay, then this point is mapped to U by f. So since this U as a function of x, y, z is this composition, so if you want to compute the derivative of U with respect to, say, x, how to compute? du dx. So du dx by the trend law, from the trend law, this will be the partial derivative of f, which respect is the first arguments, first variables, we denoted by f1. Then multiply the first first argument, taking derivative which with respect to x, plus the partial derivative of f which respect to its second derivative, so we denoted by f2. Then the second derivative, taking derivative which x, and also the third argument, and the derivative of the third argument which x. So okay, now we compute the derivative involved here. So this is f1 copy. The derivative of xy is y plus f2 copy, and the derivative of y over x with respect to x is minus y x squared. Then f3 multiply the derivative of yj with respect to x, but y and j and x are independent variables, so yz does not depend on x. The multiplication of yj does not depend on x. Therefore, the derivative of yj with respect to x is 0. So we conclude that the derivative of u with respect to x, the partial derivative is yf1 minus y over x2 x squared f2.